All right, so let's see how I do it this time. This would be kind of cool. You can go up on YouTube and you can watch 3 videos that all start with the same problem. And you can see, oh, this is Mr. Cocker's first block. And then here's his third, and here's his fourth block. See how I changed during the day. That would be kind of neat to see. I may even go up and watch it and see. So that would be kind of cool. All right, so in the problem, they are saying they want you to find the center of mass of, first off, the Earth-Moon system, and then the Earth, Moon, and Sun system. And so it's a center of mass problem. So right away I know that my only y is going to be a diagram, right? No words at all. And I'm looking at the rubric like we had in the example problems, right? To see whether or not I do it correctly. So let's draw a diagram. Let's see. I think I'll start off with we'll put the Earth here, and we'll put the Moon right here. That'll be the Moon. And then we need another system. We'll do the Sun here. We'll do the Earth here, and then we'll do the Moon over here. All right? And so I know that because I've peeked ahead, and this is the 3rd time I've done this problem today, I know that they want it during a full moon, which is that arrangement, so I was able to do my diagram ahead of time. So this, let's see. The mass of the Earth would be here in my diagram. The mass of the Moon would be here. Mass of the Sun would be here. Mass of the Earth would be here. And mass of the Moon would be here. They also tell me in the problem, in this first case, to use the Earth as my reference point. And in the second case, they tell me to use the Sun as my reference point. They don't really use the word reference point, but to say set x equal to 0, which is the origin, which is the reference point. Remember, all locations have to have a reference point. I think that was maybe 3rd day of class this year, but so that's a long time ago. So that means all my distances are measured from there. So I would have from here to the Moon would be the radius from the Earth to the Moon. Kind of like from here to the Earth would be the radius of the Sun to the Earth. And from here to the Moon would be the radius of the Earth to the Moon. And then, of course, this distance would be those two combined, right? Radius of Sun to Earth plus the radius of Earth to Moon. Right? Yep, but I'm not given that value. So I'm kind of planning ahead a little bit. I'm not given the radius of the Sun to the Moon. Easy, always. Okay. So the only thing I haven't located on here is where the center masses are. Any suggestions of where you think, just your gut tells you it's going to be between the Earth and the Moon? Huh? I just couldn't hear you.
In the middle between them.
In the very middle? Okay, let's put it there.
Actually, no, it might be
more to the Earth side. Like, okay, I'll start in the middle. You tell me when to stop. Okay, so we'll put it right there. That would be the center of mass of that system. Where do we think it is on the Sun, Earth, Moon?
I feel like it's very close to the Sun.
Like here?
Yeah.
Okay. Let's go with it. Why not? So from the Sun to that point would be x cm, and from the Earth to that point would also be x cm. I'll let that sink in for this before we head into the series, into the house. All right, good. So, we want to do the first part, part A. First thing I need to do is have that valid physics equation. So, since it's a center of mass problem, how many equations do I have to pick from? One. The one listed under center of mass, right? So, XCM equals M1, X1 plus M2, X2 plus dot 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 dot, M to the N, X to the N, over M1 plus M2 plus dot 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 plus M to the N. All right, let's do that for part A then. How many objects in part A? 2. So we only need 2 terms in our equation, right? That's what it means by that infinite series. So we're looking for where the center of mass is. We have that marked. Which object do you want to call object 1, the Earth or the Moon? Earth, okay. So the mass of object 1 would be the mass of the Earth. Now the question comes, how far is the center of mass of the Earth from the center of mass of the Earth? 0. And then our second object would be mass of the Moon. And how far is the center of mass of the Moon from the center of mass of the Earth? Well, radius Earth to Moon. All over mass of the Earth plus mass of the Moon. Oh, and we know every value there, so you guys can do that. You don't need me, right? Any questions? Excellent. Let's go on to part C then. Part C, we have the 3 objects. So we're going to need 3 terms in our XCM term. Let's take, what do you want to take as object 1?
We don't know what part C is, right?
Well, part C is defined for the Earth, Moon, and Sun.
What's the
A multiple choice question. All right, I'm going to just go ahead. I'm going to use the Sun as the first object, so it'll be 0 away. Use the Earth as the second object, so it'll be Earth to Sun away. And then use the Moon as the third object, and it will be radius of Earth to Sun plus radius of Earth to Moon away, as shown in the diagram. All over mass of the Sun plus mass of the Earth plus mass of the Moon. I agree. Let me know if you have questions or when I can move on to number. So we're doing number 10. And it's a gravity. Oh, folks, near the end of the block. Let's see. What time does the block end?
49?
49. So like 40, probably 40 something, 44 maybe, or 40 before then. There'll be an exit ticket that comes up in classroom. Please make sure you do the exit ticket for today. Ideally by the end of class. Alright, we got 2 bowling balls at rest on a rack 0.37 meters apart. And they want to know the force of gravity pulling each ball towards the other. I'm going to assume that that 0.73 meters is from the center of each bowling ball. Because if I don't assume that, and I assume it's surface to surface, I don't know how big the bowling balls are. Right? So, I'm going to assume that they're trying to make my life easier, even though they don't say center to center. So, let's see. I want to start off showing my understanding of gravity. But I have to, so I need to show, oops. That's what I need. I need to show a clear understanding of physics, links to problems to sketch a roadmap to the how, and put in all the equations I can. Right? No.
No, you don't know the equation. You can't put equations in the Y.
Don't put equations in the Y. I think I'll do a diagram though. Oh look.
Why?
Bowling ball. Bowling ball. What do I know about those two forces right away?
They're equal.
How do I know they're equal?
Forces always come together.
The forces must be equal since forces always come in pairs. What's creating this interaction? Gravity is the interaction. What's creating it? Gabe, what's creating this interaction? Oh man, sorry. I called you because I thought you'd have it. You thought you'd have it. I didn't mean to embarrass you. Go ahead. You work on number 5. That's fine. That's completely okay. Anybody? What creates this gravitational interaction? That is the gravitational interaction. Mass. Thank you, Mr. Long. You are an outstanding person. The mass is of the bowling must create this interaction. We call grav force. Anything else influence the gravitational force? I mean, this is a great opportunity, right, to look at the Y that you wrote and compare it to the Y that I wrote and see, you know, how many points would I have gotten on this one as you prepare for evaluations on this and making sure you understand it. Anything else come into play when we're talking about gravitational interactions? We just mentioned about that. Say it again. Distance between what? What point on the two objects? The center of masses. Excellent way to put it all together there, guys. So, the distance between the center of mass of each ball to the other determines, how about, the interaction. And now I write lots of equations in there, right?
No.
Oh, okay. But I want to put equations in.
Yeah, you put them in how you want to put them in.
Oh, okay. I can put them all the ones I want in the house? Okay. I'll do that then.
That's all the ones you need.
Any questions on there? We good? Okay. Oh, now I can do my equation. I can look at my equation sheet and say, oh, there's one about gravity. And I looked up the universal gravitational constant too. Yeah, got those from here, right? Wait a minute, I see this one, but I don't see the universal gravitational constant.
Okay.
Oh, it's on the next page?
Yeah.
Oh. Yeah, there it is. Which object do you want to call object 1?
One going left.
Okay. Mine is 6.4 kilograms. Oh, look it, I'm substituting with units. And then 7.9 kilograms. And then the distance between their centers for me is 0.73 meters squared. Let's see, I have my constants in Newton meters squared per kilogram squared. I got kilograms, I got meters. I'm good. Now it's all calculator work, right? Alright, so we're going to do number 12. And it's another gravity one. But it's asking about at what altitude above the Earth's surface is the gravitational field strength equal to little g over 9. Well, I know that when they say little g like this, what they mean is the gravitational field strength at the surface of the Earth. It's just a number that we use so often that rather than write it every time they choose, they're lazy, they just write little g. But I know little g in general means gravitational field strength, but that's why they write this out, but they use the character here. So if I look at my equation sheet, that darn useful thing, I have the little g that's on the surface of the Earth is 9.81 newtons per kilogram. All right? So, let's see, things I know about gravity, gravitational field. The grav field is created, in this case, by the mass of the Earth. The further from the center of the Earth the weaker the grav field. At the surface of the Earth, little g is 9.81 newtons per kilogram.
You're not allowed to put that in the equation.
It's not an equation, it's a definition. And I didn't say that I'm putting it in there to use it. It's one of the backing up facts here. You're right, I did debate whether to put it in there or not. All right, good. And I'm pushing 441. Folks, that exit ticket should be live, so you can start it at any point. For my equation sheet, I'm grabbing that G, little g, the gravitational field strength is big G, mass of the planet, over how far you are from the center of the planet squared. And big G, of course, is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And as I did in the other class, I did this one. I drew this little diagram.
Can I call it Y?
It could. And from here to here, of course, that's the altitude, right? From here to here, that's the radius of the Earth. So my overall distance from the center of the Earth would be the radius of the Earth plus the altitude that I'm at. And altitude, of course, is the distance from the surface of the Earth to whatever height you're talking about. And that's what they're actually asking me to find. So they tell me the little g, the gravitational field strength at this point, is 9.81 newtons per kilogram, because that's what it says, surface of the Earth, over 9, I think. 9, yep. That's going to equal 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared, times the mass of the planet. What planet are we talking about? Earth. Mass of the Earth, 5.98 times 10 to the 24th. Kilograms. Over how far I am from the center, which is the radius of the Earth. Radius of the Earth. Wow, this equation sheet is helpful. 6.38 times 10 to the 6 meters, plus my altitude, all that squared. Solve for altitude, which I know you guys can do. Most common mistake will be to forget that square term. The radius of the Earth plus the altitude, the whole thing squared. 6.38 times 10 to the 6 meters from on your equation sheet. All right, I will